Okay, so it's a great pleasure for me to be here all day in South Africa. So indeed, I would like to talk about string theory and non-relativistic gravity. Now we all know what string theory is, but let me make a few remarks about non-relativistic gravity, what I mean by that. So just a bit of history, which we all know, is that the earliest theory of non-relativistic gravity was introduced by Newton many hundreds of years ago, and that's what we call Newtonian gravity. And that works quite well, but there are a few notable features. The interaction, the gravitational interaction is instantaneous, there's an absolute time, and also what is important is that these laws of Newton, they were never formulated in an arbitrary frame. They were only formulated for frames that are attached to the Earth, so they are in a constant acceleration with respect to the inertial frames. So it's for a restricted set of frames that the laws of Newton were formulated. And well, with these laws they worked for many years, but then in 1905 came Einstein, and he formulated this theory of special relativity theory. And that theory, one of the consequences that it didn't like instantaneous interaction, because it would not, the speed of information should always be less than the speed of light. So Einstein didn't like Newtonian gravity, and that's why 10 years later, Einstein in 1915, he came up with this theory of special relativity theory, of general relativity theory. But it's important to notice that what Einstein did when he formulated this improvement of Newtonian gravity, that he did two things. One is that he made the theory consistent with special relativity, and that he achieved by extending the symmetries, connecting inertial frames from the Galilean symmetries, which are characteristic for Newtonian gravity. He extended it to the Poincare symmetries. So in that sense he made the theory relativistic. And another thing is that, as I said, these laws of Newton were only formulated in a restricted set of frames, and he realized that in order to do it in an arbitrary frame, you have to be in geometry. So he was able to formulate his laws of gravity in an arbitrary frame. And for that he needed geometry, and to be precise, he needed Riemannian geometry. So, but if you think about it, I mean, these are two things which are independent. This question of can you formulate the laws of physics in an arbitrary frame, you could also have asked to Newton. And so once Einstein found the trick that you need geometry, it was a legitimate question, of course, to ask, can you not go back to, forget about making the relativistic, but can you now reformulate the laws of Newton in an arbitrary frame, and what kind of geometry would you need for that? And the question is easy to ask, but it still took 8 years, and it was in 1923 that Tom, in 1923, he gave a reformulation due to gravity which was valid in an arbitrary frame. And that's what we call Newton gravity. So, and as I said, he also formed an arbitrary frame, and for that he needed a geometry which goes under the name of Newton-Cartan geometry. And you could say, roughly speaking, the difference between Newton-Cartan geometry and Riemannian geometry is that if you could represent Newton-Cartan geometry by a bread which is sliced, it's just an analogy, so that if you have, let's say, this bread represents all events in the universe at all times. So if you have two particular events and they are in the same slice of bread, then they happen at the same time. So in Newton-Cartan geometry, there's this slicing of the bread, and it's known that the two events happen simultaneously or not. And the idea of Riemannian geometry is that it's also bread, but you have not yet sliced it. So, and that means that if you have two events, say, take the same events, that it's not clear whether they are in the same slice, because you still have to slice the bread. So you would slice the bread like this, and then you would say these two events happen at the same time, but you could also slice the bread like this, and then the two events would not happen at the same time. So this Newton-Cartan geometry will play an important role. And there has been a kind of renewed interest in this Newton-Cartan geometry, And why is that? Well, there are several reasons. Let me see. So one motivation of why this new quantum gravity has been in the last 10 years has received renewed interest is that it is used in effective field theory. And in particular by condensed matter people. So they have field theories to describe models, and many of these models are non-relativistic, and they couple this then to non-relativistic gravity, and they use it not in a way like we do to describe gravitational force, they use it as response functions. So they can then, so for instance, this is a long history, and it really took off this renewed interest with work by Son from the Chicago group. And they, for instance, they showed that they applied on several models like the fraction quantum Hall effect, and they could do very nice things with it. Because just mere fact, for instance, that you want to couple this effective field theory to the new quantum gravity, well, that gives restrictions on certain coefficients in the effective field theory. There are high derivative terms, and you cannot just couple any term, and they really can do, they can derive nice predictions. And there's a lot of other questions you can ask them about these models, and there's a whole community in condensed matter who works on that. We organized also last year and the year before some workshops with condensed matter people to discuss these issues. So that's nice. Another thing that also which I just mentioned as a possible application, if you combine non-relativistic gravity with supersymmetry, so you do non-relativistic supersymmetry, then you can also consider non-relativistic supersymmetry in curved backgrounds. That's possible. And in the same way that the relativistic supersymmetry and curved backgrounds can be used for localization to calculate exact partition functions, it would be interesting to see whether you can do the same thing to get partition functions for non-relativistic theories. It's, by the way, amazing that if, I mean, the supersymmetrization of relativity is well known, that's called supergravity, and there are maybe more than 6,000 papers on supergravity. But if I ask you, give me one paper which contains the super Newton, the supersymmetrization Newton, and it just doesn't exist. It's just not done in 4 dimensions. So this whole issue is not yet well developed. But one motivation which I have in mind, which I want to continue to discuss today, is if you discuss non-relativistic holography. And non-relativistic holography is, well, most of the literature, the way people go non-relativistic is that the conformal field theory becomes non-relativistic, but the gravity, the bulk states relativity is just that they consider not maximally symmetric AES spacetimes, but other spacetimes which have non-relativistic isometries, but it's still relativity. So they consider, like, for instance, typically Lipschitz spacetimes or Schrödinger spacetimes. So that is most of the literature, that you keep relativity bulk, but you look to spacetimes which have non-relativistic isometries. But there's also a much smaller part of the literature is about the possibility, and that's much more tricky, so I will not say too much about it, but that you consider also in the bulk non-relativistic gravity. And that non-relativistic gravity should then be related as to the low energy limit of some non-relativistic string theory. And there has been some, I should say, there is already old literature about non-relativistic strings in flat backgrounds. There are papers by Gomez and Ambour in 2001, and Danielson, Josa, and Kuczynski. The motivation to study that was the days of the BMN limits, so people were looking to limits of string theory where you could have things better under control, and one of these limits was then possibly the non-relativistic limits. So there's quite some literature around these years where people work out the properties of non-relativistic string theory in flat backgrounds. And later, there's also an important paper in 2009 about Bacci and Gokukumar, who in fact investigated this possibility, and they argue that if this would work, if it's an holography related to this, then also you could quote different parts of conformal field theory with different symmetries, not Lipschitz symmetries or Schrödinger symmetries, but for instance, infinite dimensional Galen conformal symmetries. But what I want to do in this talk is just give this a chance. I mean, there are many questions to ask which are still can be answered, but what I will discuss today is how do you write down the non-relativistic string theory, what's the analog of the non-relativistic pole convection, and what is the geometry that is essential. And it turns out that geometry, it's non-relativistic gravity, it's not quite new to the quantum gravity. There's a twist. It's more subtle than you think. So and what my strategy now is to, most of these subtleties which arise here I can explain by just looking to a particle. I don't need strings. So I'll discuss the geometry and the actions for particles, and once I've explained all the subtleties, then it's very easy to go to strings. It's just the formula that become more complicated, and of course there are some essential differences, but the whole idea can be explained by using particles. So that is what I would like to do now. Is there any question at this point? Because I want to discuss now first Newton-Guittard geometry and particles as an introduction to strings. So Newton-Guittard geometry. So if you had in the non-relativistic case, inertial frames are related by Galilean symmetries, and what are they? You have type translations, generators A, you have spatial translations, so let's take four-dimensional space-time, A is 1 to 3, but most of what I say doesn't matter whether you are in four in all dimensions. And then there are boosts, Galilean boosts, and there are spatial rotations. And in fact, these are the same symmetries as in the Poincare. The most important difference is in the boost, that's why they are called Galilean boosts. Because the difference is that in the Poincare case, under boost, time goes to space, space goes to time, because time is not absolute. And in the Galilean case, you have only that space goes to time, but time doesn't go to space. Otherwise, also you would need a factor of c, the velocity of light, so that's the big difference. And it also means that this is not a rotation, but it's a translation. That makes the Galilean algebra also much more complicated to study than the Lorentz algebra, where everything is just a Lorentz rotation. Now, already is here a problem, or a subtlety, namely this in particular, and that's the difference with the Poincare algebra. If you look to the commutator of a Galilean boost with a spatial translation, then that is 0. And there are several reasons why that is not the case, should not be the case. One reason is that I have not yet discussed particles, but believe me, if you write down the simple action of a magnetic term for a non-relativistic particle, that is just x dot squared for the spatial coordinates, then the Lagrangian is not invariant on the boosts. You cannot make this boost manifest invariant because it's not a rotation. It's manifest invariant on the spatial rotation, not on the boost. But the point is that the Lagrangian varies in the total derivative, so the action is invariant, but it means you get modified Newton charges, and if you do the calculation just for a free particle, you'll find out that here occurs a central extension, just because Lagrange is not invariant. Another reason is that you like here a central extension, is that this is very strange, because if you take a massive particle, so note my argument only applies to massive particles, with a certain spatial momentum, PB, then I could not go to a rest frame by applying a boost, because it commutes. So that's very strange. So what people, that's one of these things which go a bit different than in the relativistic case. But to make a long story short, the Galilean algebra is not good enough. You have to replace this by GAPB. It's delta ABZ, where Z is an extra generator, we call it the central charge generator. And then we call it the Barton algebra. So Barton algebra is the central extended Galilean algebra.
Is the total mass of the system?
What?
Z as interpretation of the total mass?
Yeah, this Z is related, my argument also applied to a mass particle, is the dimensional mass. It's related to mass. Yeah. But okay, if you do that, then in principle, you have the Barton algebra, and then you can apply a certain gauging procedure, which you associate to these different generators gauge fields, and like you can do it also for the Poincare algebra. And then what happens is that the basic data of Newton-Guittard, the gravity of geometry, are described by a time-like vierbein, described the time component of the vierbein, and that is invariant under spatial rotation and boost. And this serves as a clock function to measure time, and it's a spatial vierbein. And that you see, it's an A, this transforms into spatial rotations, manifested just a vector, that's okay. And under boost, it transforms to the clock function, the tau. So note again the asymmetry. Yeah? The tau doesn't go to E, the E goes to tau. That's because it's a Galilean boost. But then, and that's the unexpected thing, there's an extra gauge field, which somehow you would not expect, but it's there. And that's the gauge field corresponding to the central extension. So that's the gauge field of the central charge. So sigma is the parameter of the central charge. And under the Galilean boost, it sometimes takes over the role of the tau, and that does transform to E. And concerning the other gauge fields for the boost and space rotations, light and generativity, they are dependent. You can impose constraints and then you can solve for these guys in terms of these independent fields. So these are the only independent fields. The only thing is that you solve it not in terms of only the timeline and space of hereby, but it also contains this central charge gauge field. There is a simple reason for that, because if you ask yourself, can you make out of these two fields, these gauge fields, using only tau e so that they transform in the right way in the boost, it won't work because you miss your term with respect to generativity. That's why it doesn't work. And then this guy takes over. So you add a few m terms, the curl of m, so it's being very central charge, and then there are extra boosts, and then you can make nicely transform into boosts. So these are dependent fields. That's nice, and these fields we will use if I construct my non-relativistic Bergshoeff action, these guys. And they are just dependent, they will not play a role in my story. But there is another thing which complicates life, and that is to write down an action, I need a metric. But unlike generativity, where you have one non-degenerate remaining metric for the whole space-time, there is no such thing in the non-relativistic case. Instead, we work with two degenerate metrics. See, what the point is that if you, these tau and e are vierbytes, in generativity you just take the v by squared, and that's the metric, and that's manifestly invariant with the Lorentz rotations. It's again this boost. I mean, it's not obvious that if you would say that it's invariant with the boost. And, well, in some sense you have one metric, that's the metric for the time direction, that is tau mu. Now, that's invariant under all the Barton symmetry, simply because delta tau is 0, so that's easy. But here there's a problem, because if I would do the same thing for the A, then it doesn't work, because it will not be invariant to the boost. So if I would write down an H mu is E mu A to use as a metric in spatial directions, then that doesn't work, because you can easily see that the delta and the boost of this H mu is not equal to, is not 0. So this thing, this sounds reasonable, is just not invariant under the boost, so you can't do it. But what people do in the literature is that what you can do is you can write down a metric with upper indices. So that's the E mu A, E mu B, delta AB. And it turns out, and I'm a bit quick here now, but I don't want to introduce too much details. So you can introduce also the inverse of these guys. They are just the same inverse like in generativity, where they decompose time and space. And they are orthogonal, so time is orthogonal to space. So there are relations like tau mu, E mu A is 0. And then you can show that although the E here is not invariant to the boost, that's the problem, that the inverse E is invariant to the boost. So this guy is okay, but it's fine, but it's not good enough, because in writing down an action, we want to have, in a kind of polar action, we want to use this guy. So for the time it's okay, this is invariant, but it's not invariant to the boost. So there's a problem. So what we do then is that although this is not a good metric, we use a different metric, which again is not really an official metric, but I will really, it's good enough for our purposes. It is the combination of this H mu. And now I use this extra M field, this central charge gauge field. I add here a combination, tau mu, M mu. Because remember, the M also transforms into boost, and if you do it in a clever way, the fact that this first term is not invariant to the boost is cancelled by the boost variation of this M. So this is boost invariant. So you think now I have a metric, but no, that's not true, because you just have traded in the one column for another. This one is not invariant under the central charge. Because remember, M is a gauge field. So you have either you work with something which is not boost invariant, or something which is not invariant in the central charge. But this we like much more, because remember, what will happen is that this metric, in some sense, our Bergshoeff action also will not be invariant in the central charge. It will be invariant up to a total derivative. So the non-invariance of the central charge will result in the fact that our Lagrangian is only invariant up to a total derivative. But that's good enough. So that's why I will use that as the thing which later will occur in my Bergshoeff action.
In the radiation of the NU field associated with this central charge, don't you have a piece which is the parameter of translation and then the gauge field associated with the boost?
Say it again.
In the radiation here, you have a piece which is the boost.
I skipped here a little detail because of lack of time. Strictly speaking, based on certainty, which I wanted to avoid, but now you start to talk about it, that basically these are, officially, these are the gates of what we call the p-translations of the algebra. This one is the analog of this one. Is that your question? Where are they?
Maybe my question was more humble is that in this transformation law, don't you have a piece which is also lambda A related to the translation times the field contracted with the gauge field associated with the Galilean boost?
No. So what I forgot to say is, I should have said, is that these things are all, with respect to general coordinate transformations, covariant vectors. So under general coordinate transformations, they transform as covariant vectors. And then it's under the spatial case, boost in this way, there's nothing else. So I don't know what you want to add, but there's nothing else.
No, just that there is a gauge field that I miss, which should be associated with the Galilean boost.
No, because they are dependent ones. Like in relativity, these are the spin connections for Galilean boosts and spatial rotations. They are gauge fields, but they are dependent. Like in relativity, the Christoffel symbols are dependent. And they act like the gauge fields for boost and spatial rotations.
Because there's H, P, G, and J.
So these guys lead to these omegas. The gauge fields of these generators are the spin connections, which are always dependent fields, they're not independent. So here I only wrote down the independent fields of Newton-Coulomb geometry. So they are dependent fields, like in relativity, the spin connection is a dependent field.
Once you write the portion,
what?
Once you write that portion, is zero.
I have to, as I said, I have to impose certain constraints to solve that. And the standard one is that I take certain curvature constraints equal to zero. That is, it's a standard procedure, which I've skipped here, but believe me, you can do it. Now, in other words, so what we will use later is this tau, that is the metric in the time direction, and although it's not perfect, we will use this metric for the spatial directions later in our action, and that this lack of inverse central charge will mean that we have a Lagrange which is only invariant up to a total derivative. That's good enough because the action is then invariant. Now, but okay, this is the geometry, so now also what's the action? And then also some subtlety occurs. So let's derive the action for a particle by taking a limit. So what I do is that I take the relativistic number Goto particle, I use the terminology of strings, and I take the limit, and I want to see what's the non-relativistic number Goto particle by taking the limit. Yeah? Is it okay?
No, I don't. It's right here.
What?
No, I got it, that's fine.
I can erase?
I got it, I can erase and ask question afterwards.
So I discussed now the Newton-Coulomb geometry. There are three fields. The surprise is this extra vector field. That somehow is a surprise, but it's really there. And really will need it, as we'll see. It's not just for fun. And now I want to discuss the action of a particle. And let's consider the number Goto, what we usually call the number Goto strict that I do for particles. That is this guy. That is minus m integral. I integrate over a world line. And I have embedding coordinates which occur non-linearly, like minus h dot mu, and this is the metric of generativity. I use now head for fields of generativity, because I'm going to take the limit. If the head leaves, I have a Newton-Coulomb field. So head fields means are the fields before taking the limit, they are the fields of generativity. Now, if you try to take the limit in the target space, not in the world line, in the target space of this guy, to get a non-relativistic number Goto action, it doesn't work, it blows up, you get an infinity. And one way to cancel that infinity is you are going to use now, it's a trick, I'm going to add the generativity. You see the point is that if I take the limit, this guy basically is going to give me two of the fields of Newton-Coulomb geometry, the tau and the e, but not the m. And I'm going to use now, I'm going to add the generativity in a field, and it's really an auxiliary field, doesn't describe degrees of freedom, called m hat mu, and I couple it to the particle via the Wessel-Newton. And this has a zero flux. It's really it's not like a Maxwell particle, it's just an auxiliary field. And if you do that, then you can show that if you take now the limit, that the infinity here cancels against the infinity there. So the limit you can take by taking you rescale the fields of generativity, So I express everything now, the fields of relativity. With the head, I express in the fields of Newtonian gravity, with an omega contraction parameter, basically the velocity of light, and that I take to infinity at the end. So first a subscript take to infinity, and this is my ansatz. And that gives a finite answer. And E hat mu A is just E mu A, don't do anything. And the M hat in this West-Newton term, I rescale omega tau mu. And the mass is also rescaled. And as I said, then the infinity here cancels against the infinity there. And what you end up with is the non-Goto action of a non-relativistic particle. So now non-relativistic. And it looks like follows, because you expand the square root, also the square root disappears, that's one thing, but the nonlinearity remains. It is m over 2 integral d tau times h dot mu, and now we use this h mu occurs, remember this h mu, so that contains both this guy and this m field. And this is divided by tau rho h dot rho. And that's it. So what you see is the square root has disappeared, but the difference is really that this is nonlinear in all directions, because the mu is all directions. And what has happened here is that this was the spatial metric. So so if you distinguish now between the part, these are the directions transfers to the particle, the spatial directions, and the time direction are called the longitudinal. Then you see that the embedded coordinates, the transverse embedded coordinates, the action has become bilinear, so the nonlinearity has disappeared. And in the longitudinal, the time direction is still nonlinear. That's the big difference. Here, this is nonlinear in all directions. This is bilinear in the transverse and only nonlinear in the time direction. That's the difference between the relativistic Mandelstam and the non-relativistic Mandelstam. Now is something else happens now, that this is fine, but suppose now I want to have a Polygraph string. So this, I know I can write as a Polygraph particle by introducing an auxiliary einbinding in the world line. An auxiliary field, and then you couple it, then that square root disappears, and then if you solve for E, it's an auxiliary thing, you get back the number Goto. It's a standard trick. You only need to einbind, and that becomes the multi-sheet metric in the case of the string, but that doesn't work here. You can't reproduce this by using that trick, and what you have to do is that if you want to write down out the Polygraph of this, Polygraph non-relativistic, I need an extra Lagrange multiplier. So this is -1/2 integral d tau. So it's an equivalent action, d tau, and then it is 1 over E. So E is the einbind, and then this is minus h dot mu, h mu. And then I need to select an extra Lagrange multiplier lambda on the world line times tau mu, h dot mu minus me. So that's important, is here in the Polygraph formation an extra Lagrange multiplier. And you can easily see that this is equivalent to that, because if you solve for a lambda, then you get that E is solved for as 1 over m tau dot x, and if you substitute back as 1 over E here, you get exactly that action. It's a trivial equivalence. But you cannot do it. Here there's no Lagrange multiplier needed. Here you have to do it. There's no other way to do it. But at least I don't know how to do it. Now, it's a bit funny. You would ask yourself now, is this... So here I also have a Polygraph particle, and can you say now this is the limit of the Polygraph particle? And yes and no, not quite. And that causes also some, that certain things later will become non-trivial, because well, let me use this one. The situation is as follows. So I have here, let's say, at the relativistic level, I had a non-Goto particle, and I took the limit, And after n is basically neutron, this extra vector field, and then at the non-relativistic level, I have then the non-relativistic number go to particle. This was really a limiting type. This was a rescalable field, which is overgaan, then take over to infinity. It shows just that we had to add an extra auxiliary field we had to add. Now this you can write at the relativistic level as a Polyakov thing by only introducing the ion bar. So you see now an issue. This you can write, that's what I just did, as a non-relativistic Polyakov. But this contains a Lagrange multiplier. So how does the Lagrange multiplier now occurs from a limit of this guy? So how would this work? That's the question. And the way the Lagrange multiplier arises is that what happens if you take the limit of the Polyakov particle, then unlike here, there was a cancellation of a divergence. But in this case, there's a quadratic divergence which does not cancel. There's an omega squared x squared. So if you do this substitution like you did it there, your x is a black box. The important thing is that the black box is quadratic. And so if you do it here, you end up with a divergence. And now there's a little trick, and that's what explains the Lagrange multiplier, because I write this thing now as lambda x. I use an extra Lagrange multiplier, and I write it as lambda x minus 1/4 omega squared lambda squared. This is equivalent. If you solve for lambda, you get back that. It's the same. But the nice thing is that now, if you take omega to infinity, so you really have changed in some sense the definition of your limit, but this goes nicely to lambda x. And that explains in this term also the presence of the extra Lagrange multiplier. But the point is that you can't add the Lagrange multiplier at this level and then take the limit. So it is equivalent, but strictly speaking, you cannot say that this is the straight simple limit of that thing. Although this is equivalent to that, that's the limit of that, and this is equivalent to that, this is not the easy limit of that. But it is what you call the non-relativistic Polyakov particle. Maybe it's also good to say to give, because as we saw, to cancel the infinity, I had to use this extra vector field, which when I took the limit became the central charge case field, and what the hell is that the physical interpretation of that field? But it has to do with the fact that that vector field in the relativistic case couples to the conservation of particles minus antiparticles. And the M of Newton geometry, the current has to do with the conservation of particles. This central charge is nothing else than the U1 in the Schrödinger equation. So if I would take this limit not at that level of the particle, but in the second quantized quantum field theory, then if you couple a real Klein-Gordon field to relativity, you can't take the limit. You always have to take a complex Klein-Gordon field. And then, if you couple that to relativity, then this M is an increase occurs in covariant derivatives, and then there's again a crucial cancellation of infinities between the mass term and this M, and they take the Schrödinger equation. So and that has a U1. So the U1 of the Schrödinger equation is literally the remnant of the central charge transformation. The Galilei algebra is also not realized on a complex scale in the usual way. It's what you call a projective representation. It's realized up to a phase transformation, and that's exactly this U1 transformation. So you really need it to. There are no Schrödinger equations for a real field. So that is that.
And Eric, the action that you get in the end, if you go to a Hamiltonian formulation, then you compute the rigid symmetries and the algebra of the charge that will close on the Bachmann algebra.
Yeah, that will be the Bachmann algebra. Yeah. Now comes the point. So I did a lot of work with particles, but now the question is we want to do strings, and so I want to go a bit quicker. So it's basically the string story is exactly the same, but it's a bit more complicated and it's a little twist. It is different also. So first of all, if you look to the geometry, because we introduce now a Newton geometry, but you see the funny thing is that Newton geometry, the way I did it, it was really suited for particles. Because remember, I had this vector field, I coupled to the particle via this limit term. But suppose I want to take the limit of a string, then that doesn't work because I can't couple a vector to a string. I mean, I have to couple a two-form to a string. So the limit I take, that's the remarkable thing. So Newton gravity is the gravity seen by a particle, but a string sees a different geometry. This is not the geometry which I can use for a string. So I can do it. So what is the geometry then you can use? Well, as I said, the limit. So and that geometry is a slight new version of Newton geometry, and we go then to distinguish it, we go to the string Newton geometry. So and what happens is the following. remember when I took the limit of the non-Bergshoeff particle, I had to introduce an auxiliary fluxus field to relativity. And I redefined it, the omega contraction parameter, and it became the tau of the clock function. So this I cannot do for the string, but what I can do for the string, of course, I can introduce a fluxus 2 form. But you see, now I cannot use the tau because tau nu anti-symmetric is 0. So I cannot use tau. So I can simply not. And if I use tau, I will get tau nu, and that is 0. So what you do now, the string is an extra direction, a spatial direction. So what you do is that you introduce now a kind of different foliation in which I have in some sense the analog of tau becomes now tau nu a, and I do a slightly change of notation. I use a now for the directions long through the string, so it's the time and the direction along the string. And I introduce 2 of these taus, because then if I have 2 of these taus, you see then, and I hit this with an epsilon AB, then I get out to tau squared. So that's the trick, to cancel the divergence in the string case, which I also higher order because it's now a surface instead of length. I couple the string to a fluxus 2 form, but what you see is now I have to change the geometry because instead of tau, I use tau A. So basically what I do, it's really very similar to Newton-Tau geometry. You could say Newton-Tau geometry is what I did is that the flat Lorentz index in Newton-Tau geometry are split into time, this is 0 direction, and then the transverse directions, which I now call A prime. So I call it A, but I wanted to reserve A for the longitudinal direction, so that's what I call A prime. And all you do now is that this 1 and the rest. So now I write A hat, I do it differently. I write it as A prime. So where A are the 2 directions along the string, A is 0,1. So this is just 1 direction along the particle, these are the 2 directions along the string, and the rest are the transverse directions. So you make, instead of 1 plus the rest splits, you make 2 plus the rest splits. But apart from that, it is very similar. So, and they can go over the whole story of this Newton-Tau geometry, but you get extra indices. So the independent fields, for instance, of Newton-Tau geometry, they are the following. This field is very unstable. So I had for Newton-Tau geometry, I had a clock function, a tau mu A and an E mu A prime, and a center charge. These were the independent fields, the rest were dependent, and that now becomes I get now a tau mu A, I get 2 of these taus, and I get the transverse E mu A primes, they stand for the transverse vierbeiner, and I get also I get now 2 center charge gates with it. So I just get now, instead of 1 index, I have now 2 indices. That is, so it's that's really going there, and then there are some further complications which I won't mention here. What is remarkable is that you see, whereas relativity can be coupled to all extended objects, particle strings, it's the same relativity which couples to all extended objects. In the non-relativistic case, it's not the case. You have Newton-Tau gravity couples to particles. This string Newton-Tau geometry couples to strings. You need a kind of membrane geometry for membranes, because then you have to use 3 plus the rest splits, and so every extended object can only be coupled to one version of non-relativistic gravity. It also shows that another thing is that non-relativistic gravity is not unique. There's only one relativity, but you see this fact that you can do different foliations also means that there are different versions of non-relativistic gravity. Now, and so now we are very close to writing down the Polygon string. So again, there are 2 degenerate metrics, but they are very similar, like in the Newton-Tau case. There is the one for the longitudinal directions, tau mu, which is now tau mu A, tau mu B, eta AB. Eta AB is the Lorentz, 2-dimensional Lorentz metric in the longitudinal directions, and there is the kind of transverse metric which you can use, and that is just, it's the E mu A prime, E mu B prime, delta A prime B prime. But that's the thing, it's a non-boosting variant, and then you can compensate it by adding an extra term tau mu A times M mu B with delta A B, which is in the longitudinal directions. And that is then nicely invariant. And then you're almost ready to write down the action. The only thing is that for the particle I had on the world sheet, there was an einbein, but now I need a two-dimensional tribein, and so that's almost E. I use now alpha A, and then the metric, yeah, I use now H now for this thing really as the metric on the world sheet. There's nothing to do with Newton geometry. It's just the E alpha A, E beta B, eta A B. So these are all indices on the world sheet. This is the tribein on the world sheet. And furthermore, to write down the action of the Polyakov, the non-relativist Polyakov string, it's also very useful to use a like notation, which instead of E alpha A, because A is two directions, is two Lorentzian directions, you split it into what I call E alpha and E alpha bar, where one is time plus space and the other is time minus space, and same for tau mu A. A were also this is the two directions on the Lorentz index on the world sheet, and these are the two directions along the string. You also can write it's two values you can write as tau mu and tau mu bar. And then I can write down really so I've identified this string geometry as the relevant geometry for this non-twisting string, and then you can write down the whole action, and that action that looks as follows.
Sorry.
Yeah.
When you introduce this extra index A, is the
Again, so
when you introduce this extra index A,
yeah.
Is the Bachmann symmetry get enhanced?
That is the
Bachmann symmetry get enhanced.
Well, it's a different algebra I have now. So I take different limits also there, because to get an let's say the Galilei algebra, you take the Poincare and then you redefine your time and space differently. But now, if I start from the Poincare, I redefine my longitudinal and transverse directions differently. So it's really, I would not call it an enhancement, it's really a different, in some sense, a different algebra. Well, there is you could say that, because you see I have here, so there is a sense there is a relation, because I have here in some sense 2 taus, and in Newton geometry 1 tau, but I could take a truncation, I could say 1 tau is taking to 1, because in some sense taking a fixed circle. And then in some sense you get Newton gravity on the microscope times a circle. So in that sense, 1 is contained in the other by truncation. In that sense, there is a relation. Yeah. And I think also the algebra, if you do specific truncation, 1 is embedded in the other. Okay. I should maybe also say that this, so the big difference is that I have this formation with an extra spatial direction, and so I have time, I don't forget the time with time and the extra circle is the direction along the string. That's very important also if you look at the spectrum. This was analyzed for flat space-time for these papers by Gomes and Oguri, because the point is that there are no momentum modes in the spectrum, because there is no element of the graviton. I remember Newton is instantaneous interaction, so there's not something like a propagating graviton, so there are no momentum modes for this is a closed string. But what you do have is wound strings, and these strings wound around that extra direction. There's an extra circle direction, so it's also crucial for to get really wound strings with finite energy. Well, it's a long story, but that is. And then these strings, they have a gravitational interaction, and that gravitational interaction is described by this string Newton geometry with instantaneous interaction. That's the way it goes. But we are now ready to write down this Polyakov thing, and let me just write it down, because it's a nice starting point for all kinds of discussions we can do. So this is now equal to the non-twisted Polyakov string is T is the string tension, and then we integrate over the two-dimensional world sheets. Then we write down first a kinetic term, where just the tribind couples in a regular way to the kinetic term. And this is the term which is bilinear in the transverse directions, like for the particle. So the nonlinearities are so the nonlinearities come if you solve for the 8, and then we'll see that's all the time directions, the longitudinal directions, and it is bilinear in the spatial directions. And then this extra Lagrange multiplier term looks a bit funny. It's epsilon alpha beta times lambda, and you see a like connotation, E alpha tau mu minus lambda bar, E alpha bar tau mu bar times d beta x mu. And then, for completeness, you could also add now really a Neveu-Schwarzschild, so not a fluxus one, a real one which has its own equation of motion, and that these labels are easy to take. You get just d alpha x mu, d beta x mu, d mu, and if you want to also get add a delta 1 over 4 pi integral to 2 sigma square root minus h r h phi. So, and if you want to go back to the number-go-to formulation, then this, the line with the Lagrange multiplier, it only contains the longitudinal directions, the tau, the dx is projected with the tau direction. And the interesting thing is, if you now solve for the lambda bar, so you say delta lambda s is delta lambda bar s is 0, that enables you to solve for the e in terms of the tau. But it is rather subtle, because what you find is you cannot show that E alpha A is tau alpha A, because these are two different indexes. A was a Zweibein index and a Lorentz index in the multisheet, and this A was just a Lorentz index in the target space. They cannot. But what you find is that if you take the metric out of these Zweibeins, H alpha beta, that's the one which occurs here only, that becomes equal to tau, the pullback of the tau mu, up to a scale factor. Up to a scale factor. And that, if you substitute that gives you the nonlinearities. This is scale invariant, so the scale factor drops out. And then here you get the tau, this disappears, and that comes to tau, and then you get, let's say, the analog of the number-go-to stream. And so this is the, now you can do, so this is a nice thing, because now you could use this as a starting point to see, well, can it make sense out of this non-relativistic string theory? I mean, can you do things which you used to do for a relativistic string? So, one thing, let me just, how much time do I have?
About just over 10 minutes, 10, 15.
Okay. So at the end of the day, I mean, I skipped a few subtleties, but what I want to say is that here there is a proposal for an action of a non-physical polygon string action. And what are the calculations you can do now? Now, one thing you can do is I knew it. Well, this is, you cannot do it anymore. Let me do this. So one thing we are trying to do, but we have not yet completed it, but you can now ask yourself, what are the consistent backgrounds of this non-physical string theory? What are the beta functions? And we have now a theorem, we will see it's scale invariant, and what happens now with beta functions? Do they give into the expected equations of motions of this string backgrounds? Well, first of all, what you have to do is that you have to set up a background field method adapted to this new geometry. For the relativistic string, people do it for the Riemannian geometry, but I'm now dealing with this string to Coutan geometry, so you have to a bit adapt the background field method to that geometry, but that can be done. But the calculation is, well, it contains two parts. You see, the parts that you have is, the spatial part is like a relativistic string, it's bilinear in the coordinates. It's not, that's also the first kinetic term. But the time direction, the longitude directions, that's this extra Lagrange multiplier term, that's a first order system. It's like an extra Gauss system in flat space. And their calculations are slightly more involved. It's also not, you see, it's not quite, as I said, this this Pauli constraint is not, if it would be a straight limit of the relativistic string, then it would be easy. I literally take the limit of the calculation of the beta function in the relativistic case, but it's not. That was a subtlety. I'm very much convinced, or I very much think, but I don't dare to publish it, but that what we then will find is that you get what you expect, namely the equations of motions of Newton's string geometry, which is the limit, is you have to take the string limit of generativity of the Einstein equations. But the calculation is not finished, and we are also using different other techniques to convince ourselves that we get the right answer. So I want to be a bit careful. It's not just to redo the calculation of the relativistic case, and it has to do with the fact that you have these extra terms which are first order derivatives with Lagrange multiplier. You really have to take that carefully and do it. But it should work. And if it doesn't work, of course, then okay, then you have a problem. Then, but I can't believe it. I very much think it will work. Now, another thing you can do is, and that we have done, is that you can now see what's the analog of the triviality rules, the pusher rules. So we know that in a string case, there is always a string can't distinguish between a circle of radius r and a circle of radius 1 over r. And can you do that calculation? And there are several ways to do it, but one way is to do a kind of duality transformation of the world sheet where you place a scalar by a dual scalar, and then you see what the dual scalar kind of the dual geometry it sees. And there this funny thing happens because it depends whether you do the duality in the long-term or transverse directions. And it has to do with the fact that this Lagrange multiplier is only sensitive for the long-term directions. So if you do duality in direction transverse to the string, it doesn't see this Lagrange multiplier term. And then you find also basically, you do the same calculation as you find the Bushy rules, just R1 to R. But if you do something funny happens if you do duality in the long-term direction, the spatial long-term direction, then the calculation changes because that sees the Lagrange multiplier term which contains a longitudinal coordinate. And what happens then if you try to eliminate you interchange your coordinate for a dual coordinate, then this Lagrange multiplier occurs in the solution, and you get a term which is quadratic in the Lagrange multiplier, but then it's not a Lagrange multiplier anymore. You can solve it. And this Lagrange multiplier was the signature of a non-relativistic string. So if it disappears, you get all the features of a relativistic string. And the funny thing is, what happens is that if you take this non-relativistic polygon string and you trivialize it in the non-relativistic direction, you get a relativistic polygon string coupled to generativity, but it has a like direction. So there's in the dual direction, if y tilde is the dual direction, if you dualize, then the metric there is 0. And that smells a bit, these things, these assumptions have been made by people who do discrete Lightning quantization of string theory. So somehow, well, this has to be investigated further, but there's somehow a relation between this non-relativistic string and approaches to discrete Lightning quantization in the relativistic string theory. I should, by the way, say that the fact that you have this null direction secretly also hides, makes it non-relativistic, yeah, because if you would reduce along this direction, you get non-relativistic, something with non-relativistic symmetry. So if you think it's generativity, but this null direction knows about non-relativistic symmetries. So, but that's a funny thing. There's also other issues here which I won't discuss, but what the target space interpretation is. There are some funny things which I have no time to tell, but this needs further investigation. So what is the analog, for instance, of the, you can't interchange a string with a winding mode because I told you a momentum with a winding mode because I told you there is no momentum modes. And that has to do with some subtleties which occur here, which I did not discuss. But in some sense, this non-relativistic polygon string is insensitive for certain special combinations of backgrounds, and then somehow it is consistent with that observation. But this needs a bit more study. We derived the duality rules and this statement, but what exactly the target space interpretation is and how it works, that needs a bit more investigation. That is not yet under control. Another thing is that, unlike generativity, it is non-trivial also, if you derive in the relativistic case the Einstein equations as consistency conditions, there's also an Einstein action. You can integrate to an action. But that is, in all these non-relativistic gravity theories, non-trivial, and there has already been a talk by Yang Lei on non-relativistic gravity actions in 3 dimensions. And it has to do with the fact that if in the way I presented it, you should remember, if I took the limit of a particle, suppose you get infinities, and I could take care of it by adding this extra vector field in the case of a particle. and a two-form in the case of a string. But if you take, that doesn't work in the case, if you take the limit immediately of the Einstein-Hilbert action, I can't add this two-form. How do I add it? I can't add a term with a two-form just to the Einstein-Hilbert action. And there's one exception, and that is that, and then you can write down an action, and that is sometimes the analog of the three-dimensional case which has been discussed in the lecture by Jan Ley, is that if I have 4 dimensions, then, so I remember I need this two-form to cancel infinity, so the limit of the polynomial string. And now I take the limit of the Einstein-Hilbert action and get again infinities, which are I cannot cancel. But if I have in 4 dimensions, I can add a term, epsilon nu rho sigma, and then an n hat mu, so that's a two-form which I add to relativity, d rho, and now I have an extra vector field. And that vector field is also there because the special thing about 4 dimensions is that you can extend this algebra with an extra central extension, only 4 dimensions. And it has something to do, that's the interesting thing, and then you can take limits. So then the infinity of this can be cancelled by that. But besides the two-form, I need this extra vector field. That's an extra central charge, and in the same way as the first central charge was related to mass, the second central charge has something to do with spin. And the special thing about strings in 4 and particles in 3 is that the transverse direction is 2, and then you have anions. So you have to be very careful also with the string spectrum, because special things happen if you do that. The Jell analysis doesn't apply. So in some sense, what I expect that if you do this has something to do with the fact that in the spectrum, I would expect that unlike the Jell analysis, in any dimension, some of the fine strings are anionic strings, and then they would appear as anionic particles if there's a surface. So that is also kind of would be interesting. Also, if they exist as anionic strings, then in a holographic pose, they would enter a boundary and would occur then in a three-dimensional boundary where we have models where anions occur. So that is about actions. Then let me see, there are another thing which you can do is also, since I have this T-duality symmetry, I can embed the whole thing also in what we call double field theory. It looks like you can use the same formulas, and it's just that you have to use degenerate metrics, but then you can make the thing also manifest with the symmetries. And of course, to come to the final thing, I was interested in non-relativistic holography. So how much chance has this that it survives? Well, it's not that you can immediately say this doesn't work. I mean, the nice thing is that I can use this polygon string as a starting point. I don't have to use the relativistic string and take limits that I also can do, but I can use this now as an independent starting point and see what the properties are. And the question is there also a notion of a non-relativistic holography? That's not clear. There are one of the pressing questions is you see in holography you need if you want to describe finite temperature boundary theories, you need in the document solutions to the horizon like a black hole. And the question is, can you find similar things here? Now, there are no black holes in Newtonian gravity, but remember, I'm not doing Newtonian gravity, I'm doing string Newtonian gravity. That's a surface reaction, so that gives you, it's a different question. And also, there are certainly non-relativistic field theories of finite temperature, so they exist. But that's the one of the things which is still puzzling. Can you really find in this new geometry we have here, using also this extrafoliation, can you find interesting solutions which have a horizon and which could be used to play a role in this non-relativistic holography? So that is still, I don't have much to say, but it's interesting to investigate. So I think the most important message of my talk is that I did present to you, after a lot of discussion, a reasonably simple action of a non-relativistic string coupled to a new geometry, the string geometry, and that you can use as a starting point to investigate what these properties are. At least you have something in your hands and you can discuss it, and you can investigate it, and maybe it has nice properties, maybe it has some properties which you don't like, that the future will tell, but at least it's something concrete and you can look at it. That is the end of my talk.
Okay, so there's time for some questions. Yes,
You just saw the classical questions in motion on the string. Do you have a speed of light for propagation, or does that depend?
There's no, in the target space I took the limit, so there's no speed of light in the non-relativistic reality. There's no speed, on the world there is a speed of light.
Yeah,
So I didn't take
does
the,
it depend on the central charge? Or
well, there I have a relativistic world sheet, so in this calculation with this Gomez and Oguri did, they take the limit only in target space, and then in the world sheet is relativistic, and then you can do the analog of the usual calculation, the string theory. If you take the limit there, which sometimes people do, then you really cannot use it as an independent starting point. Then you get some strange, horrible things, which I don't know what it means. So people have done that, but that you should not do that. I really only take the limit in the target space. So I just have waves on the string world sheet still, with a velocity of light.
but that's determined by the central charge, right?
The center charge of the
Yeah, of the Newton Cartan, right?
the velocity of light is
So-
the
so-
center. You mean the
so-
center charge and this mass parameter?
Yeah.
But that was a mass parameter. That was a target space thing. And this whole Newton Cartan, that lives in the target space. That's the job of the target space. Now we talk about velocity. Well, maybe we should
Yeah,
talk
okay.
more. But,
Any other questions? So let's Okay, so we'll resume at 2:30 for the last talk.